Our numbers up using unit building blocks. 3, 4, 5, 6, 7, 8, 9, 10. Now we can use our tens to build up to 100. 20, 30, 40, 50, 60, 70, 80, 90, 100. We can now build up to 1,000. 200, 300, 400, 500, 600, 700, 800, 900, and the next number will be 1,000. Because of the manner in which we built our numbers, we create a structure which enables us to simplify their representation and manipulation. A distributive property was part of that structure. 300 is 3 100 blocks, 40 is 4 10 blocks, and 6 is 6 unit blocks. That's 3 times 100, 4 times 10, and 6 times 1. That could be written as 3 times 10 to the 2, 4 times 10 to the 1, and 6 times 10 to the 0. Someday we will learn how to understand the following notation. Let us build ourselves a scale using rulers. First, we put the rulers in place. Then we put our balancing weights at the 0 marks. Our scale is ready. Let us measure the weight of 258 grams. We move the 100-gram weight to position 3. Oops, too heavy. We move it back to the 2 and record 2 times 100. Now we move the 10-gram weight to the 6. Whoops, again. We move it back to the 5 and record 5 times 10. Now we move the 1-gram weight to the 8. It balances. We add the 8 times 1. That's equal to 258. 2 times 100 is 200. 5 times 10 is 50. And 8 times 1 is 8. 258. We have learned that the concept of a ruler for measuring could be applied to measuring weight. We applied our knowledge and understanding of a simple balance to build and use a complex one. As a reminder, the product of the weight and the distance on one side of the fulcrum is equal to that on the other side. We learned that the scale and the number structure have a one-to-one analogy. Next time we go to the doctor's office, we will know how to use the scale. If you want to be a doctor, you have to know this area of math and physics. Science is as much about what we did not learn as what we did learn. We did not learn how to calibrate the scale, and we did not learn how to determine the error in our measurements. Math is required to calculate the correct length of the arms of the scale and the size of the balancing weights. The measured weight is not necessarily exactly 258 grams. We use the weights 1, 2, 4, and 8. To weigh a 1-gram weight, we just need the 1-gram weight. To weigh a 2-gram weight, we need a 2-gram weight. However, to weigh a 3-gram weight, we need a 1-gram weight and a 2-gram weight. And we see in the number there, 1-gram weight and a 2-gram weight. To weigh a 4-gram weight, we need 1 4-gram weight. We don't need any 2-gram weight or 1-gram weight. However, to weigh 5 grams, we need a 1-gram weight and a 4-gram weight. So we see a 1 in the 4 position and a 1 in the 5 position. To weigh a 6-gram weight, we need a 4-gram weight and a 2-gram weight. 2 plus 4 is 6. To measure 7 grams, we have to add another gram. 1 plus 2 plus 4 is 7. And we see that we have a 1 for each one of those weights in the 4, 2, and 1 positions. To weigh 8 grams, we need an 8-gram weight. So we see a 1 in the 8-gram position and a 1 in the 4-gram position. The following table gives the binary numbers we have to use from 1 to 10. 1 is 1, 2 is 1, 2, 3 is 1, 2, and 1, 1, 4 is 1, 4, 5 is 1, 4, and 1, 1. And we continue up to 10, where we see a 10 is an 8 and a 2, a 1 in the 2 position, and a 1 in the 8 position. We would like to convert that binary number to a base 10. We can rewrite that number as 1 times 2 to the 7th power plus 1 times 2 to the 3rd power plus 1 times 2 to the 1st power. We rewrite that binary number using decimal numbers. 2 to the 7th is 128, 2 to the 3rd is 8, and 2 to the 1st is 2. We now perform the multiplications and add the numbers, and we get 138 in the base 10. We would now like to convert the 138 in base 10 back to base 2. We can write this number as 1 times 10 to the 2nd plus 3 times 10 to the 1st plus 8. We rewrite as 8 plus 10 times 3 plus 10 times 1. We then rewrite each of those numbers in binary. The 8 is 1, 0, 0, 0, the 10 is 1, 0, 1, 0, and the 3 is 1, 1. We first now perform the addition. We then perform the multiplication. Then we perform the addition, and we get back the original number that we started with in the binary number system. We can also convert by using division. 2 goes into 138/69 with the remainder of 0. 2 goes into 69 34 times with the remainder of 1. 2 goes into 34 17 times with the remainder of 0. 2 goes into 17 8 times with the remainder of 1. 2 goes into 8 4 times with the remainder of 0. 2 goes into 2 4 2 times with the remainder of 0, 2 goes into 2 1 time with the remainder of 0, and 2 goes to 1 0 times with the remainder of 1. We now write the numbers from bottom up, and we get the number in the binary system. Two, 3, 4. When we get 5 pennies, that becomes 1 nickel. 6, 7, 1 nickel and 2 pennies. 8, 9. Again, we get 5 pennies, that becomes 1 nickel. The 2 nickels become 1 dime. 1 dime, no nickels and no pennies. 11, 12, 13, 14, 15. We get a nickel again. We notice that we can get no more than 4 pennies because as soon as we get 5 pennies, that becomes 1 nickel. We can get no more than 1 nickel because as soon as we get 2 nickels, that becomes a dime. We can get no more than 2 dimes because when we get 2 dimes and a nickel, that becomes a quarter. We can get no more than 1 quarter because 2 quarters gives us a $half. We now can see this summarized in the table where the dime and the penny can only occur in quantities of more than 1. In this last table, we have shown the structure with our conventional number system and this money system. The number to the right in the money system is the count of the pennies. The next number is the nickels. The next is the count of the dimes. The next one, the count of the quarters. And the last one, the count of $half.
In our peppercorn universe, where the sun is the size of a peppercorn, we have plotted a logarithmic base. That way we can see all the planets on a scale. We can have the size of the planets because we're basically looking at the exponent of our numbers, and this allows us a better scale than if we were to do it in a linear format. So this is another form of number structure.